Like, all the.
Just gonna.
Oh, yeah.
I thought it would be more like. We're giving you an LTC on that. And Ryan, if you will. Oh my God. It's the same teacher, of course.
Yeah, but it might be one. And I had they were. Oh, it was so wasn't there? Can't read silver. There was a D. So it was. It must end that. It's in the T.
Actually, about the year. What makes it very sad?
Okay, so we'll get started. I hope everyone's having a good day. Before we begin, I sent out an email through Canvas today. We have a couple of students in the course that would like to do a computer science minor, but they have to take a course that conflicts with the LO1 lab section, so they would like to be in the LO2 lab section. But that's full, so they can't take any spots there, so. This is the last final request, if anyone is able to switch into LO1 to make space for these students, I'm sure that they would appreciate it. Okay, so we'll get started here in a second. I just want to look ahead a little bit. What we're going to do today is I'm going to try to convince you that you already have at least a qualitative understanding of the behavior of this circuit, which involves an inductor, capacitor, and resistor. And so this is not a circuit that you would have seen before in something like first year E&M or anything like that. Nevertheless, I'm pretty confident that we'll be able to convince ourselves that we know roughly what should happen in this circuit. Then on Monday, what we'll do is we'll take a bit of a right turn, and we're going to cover just a little bit about error analysis. Enough that you will have all the things that you need to do proper error analysis of the data that you're going to collect in the lab this term. After we've done that, we'll be ready for that first assignment. So I expect the first assignment to come out near the beginning of next week, and I'll make an announcement about that when it is ready. Okay, also, if you go to the course website, the PDF of the notes from the first two classes are there, and then the recording of the second class worked, and so there is a link now to the YouTube video. And so going forward, all of the future classes should have these recordings as well. Okay, unless I make a mistake, which I am the king of mistakes, so that is more than likely, but we'll do the best. Well, I'll do the best I can. All right, so last time we talked about the voltage across a capacitor, resistor, and inductor, and in this way, I'm worried just about the magnitude of these voltages for right now. And then we said, okay, what would happen if we put all of these components in series in a circuit with a battery? And so the idea is we're going to start with this switch. I drew the switch in a little bit of a different geometry today than I did last class. And that's because what I want to imagine is we put the switch in a down position for a long time. If the capacitor had some charge on it, when we put the switch down, that charge will leak off towards ground. And so we just wait a long time, the capacitor completely discharges, and when the charge is completely gone, there will be no current in the circuit. So that's our initial condition. Then what we're going to do is after the switch has been down for a long time, we'll pick a time, we'll call it t = 0, and then we're going to flip the switch up. And I want to know what happens when we flip the switch up. Well, we worked out already the Kirchhoff voltage loop rule. And so we just went around this circuit in the clockwise direction. We have gained the voltage of the battery, and then we have voltage drops across each of these components, and we know how to calculate all those things. And we set up this expression, which is a second order differential equation. And unless you've taken some math courses already that are at the differential equations course, we don't yet know how to solve this expression. I will tell you that what we're going to do next week, after, or maybe the week after we talk about the error analysis stuff, we will analyze this circuit again, but without the inductor. And so without the inductor, this last term will be gone, and we'll have a simpler differential equation. We will solve that one. Okay, so that one will actually solve. The second order one, we're not going to solve in this course. I used to do it, but it takes a bit of time, and you will see that solution in your math. Is it math 225? Is that the differential equations course? Yeah. And you probably will also see it in Phys 216 if you take that course next term, which is the mechanics course. Okay. But the goal is to solve for Q of T. And in this type of analysis, this is called a time domain or a transient analysis. What transient analysis means is that we're going to have our system in one equilibrium state, and then we're going to make some change, and we're going to watch it evolve into a new equilibrium. So in our example, the first equilibrium with the switch down is no charge, no current. Then we flip the switch up, and the system's going to evolve to a new equilibrium. And what we're trying to find is how does the charge on the capacitor, for example, change with time as we go from one equilibrium to the next. Once we know Q of T, then we could calculate everything else, right? Because I could take its derivative, then find the current. Once I know charge and current, I can find the voltage across the capacitor at any time, the voltage across the resistor at any time. I take another derivative of the charge or take a derivative of the current, then I know the voltage across the inductor as a function of time. So if I can find this, I can find everything else about that circuit. Okay. Later, what we'll do, the reason I emphasize this as a time domain analysis, what we're going to be primarily interested in a few weeks' time is understanding not how the circuit behaves as a function of time, but what if we replace in our circuit the battery with a function generator, something that outputs a sine wave. We're going to use function generators in the lab all the time. And what they have is they have a knob where I can change the frequency of the sine wave. And so another question that we're going to be interested in this course is how does the behavior of the circuit change as I vary the frequency of the sine wave that I drive it with? That's going to be called a frequency domain analysis. And that's where we'll spend most of our time and effort in this course. But we'll start with these time domain analyses. Okay, so the first thing I'm going to do is I'm going to rewrite this differential equation where I'm going to isolate to have, I don't want any coefficient in front of the second derivative of Q. So I'm going to just divide by L. So I'll divide everything by L. And I'm going to get rid of all the minus signs. So all these terms that have minus signs, they're going to take over to the right-hand side. And so if we do that, we can rewrite this differential equation as, okay, let's see. We're going to divide by L and move all the negative stuff over. So we'd have a dq, second derivative of q, d2q, dt2. And then we're going to have a plus, let's see, we have r, but we have to divide by L now. dq, dt. And then we have a plus 1 over c, but then we still have to divide by L. So it would be 1 over LC, and then Q. And then I'll leave the V naught on the original side because it's already positive. We just have to divide by L. So it's V naught over L. Okay, and I'm going to give this equation a label. I'm going to call it A because we're going to come back to it. I said we're not going to solve this rigorously, and we're not. I will, however, if you're interested, put notes on the course website that have the full solution to this differential equation. And so if you're interested, you could look at it. It's not required reading. I'm not going to test you on it or anything like that. I'm just there for the interested, enthusiastic students. Okay, so if you like, we can see the full solution to A on the Phys 231 website. And so this is optional, reading not required. Those notes aren't there now, but they will be there probably tonight. Okay, so we will try to demonstrate that the LRC circuit has a mechanical analogy that we already understand intuitively. The reason the LRC circuit's not intuitive is because we don't interact with or we don't encounter LRC circuits on a regular basis, but we do encounter mechanical systems on a relatively regular basis. So what we're going to do is we're going to consider a mass hanging from the ceiling by a spring. So our mechanical analogy will be a mass on a spring. And I'm going to add one more thing. The mass is going to be suspended in some kind of fluid. So we'll have the mass hanging from the ceiling on a spring, and then underneath it will be like a beaker filled with some fluid, and the mass is submerged in that fluid. The mass is also submerged in a viscous fluid. Okay, so let's just draw the picture. It's pretty simple. Here's our ceiling, here's our spring, and I'll make it a bit longer. Here's our mass M, and we'll surround this thing by some kind of fluid. So here's our fluid. And what I'm going to do is I'm going to identify the equilibrium position of the spring, right? So if I put a mass on a spring, I hang it from the ceiling, it'll stretch the spring down a little bit. It'll stretch it until the potential energy let's say until there's zero net force. So maybe a better way to say it is that the spring force pulling it up, which is K times the displacement, is equal to the gravitational force pulling it down, mg. Okay, and so maybe without any mass on the spring, maybe this is the equilibrium length of the spring. So x0 is the unstretched length of spring. Okay, so fair enough. Let's imagine that what we do is we start by holding the mass at its unstretched length. So somehow we do that, right, while it's in the fluid. And then we release it. So the question is, what is the motion of the mass? What's the mass going to do if I hold it here at the unstretched length and then release it? Just tell me what it does.
Go down.
It'll go down. Okay. Yeah. What else? Is that it? It just goes down and that's it.
Gonna oscillate.
It's going to oscillate, right? If this fluid is not too viscous, what will happen is when I release the mass, it will fall down. The spring will start to stretch and it'll store up some potential energy. As it stretches and builds up potential energy, it will lose kinetic energy, so it'll slow down. Eventually, it'll come to a stop, and then we have a whole bunch of potential energy stored in our stretched spring. It'll pull the mass back up. It'll start converting that potential energy back into kinetic energy, and this thing will oscillate. Will it oscillate forever? Nope. Why? What's going to stop it from oscillating? The fluid, what about the fluid? Yeah, friction or drag force. So as the mass is moving through the fluid, it will be experience a drag force that will always oppose its instantaneous velocity. And so that drag force is essentially taking some of the mechanical energy of our mass on a spring, the potential plus kinetic energy, and converting that into heat. As we pull heat out of the system, we have less mechanical energy, and so the oscillations become damped. They become less large, and they damp more and more and more until this thing finally comes to rest. Okay, so if we stretch and release the mass, it will begin to oscillate about an equilibrium position. The drag force on the mass due to the fluid converts some of the system's mechanical energy into heat. This dissipation causes the amplitude of the oscillations to decrease with time. So that effect is called damping. It's damping the oscillations. So we could sketch that if I was to try to draw the position of the mass as a function of time. It would look something like this. So before I draw that, let me define a coordinate system. So I'm going to choose the down position to be, let's get rid of that. I'm going to choose the down position to be our x-axis. So positive displacements are down from this equilibrium position. All right. So what we would imagine seeing then is some kind of damped oscillations, which eventually die out. Okay, and so this is the x, it's the position of the mass. If x0 is the unstretched length, then what we'll have is some equilibrium that is somewhere away from that unstretched length. Okay, so x0 might be sitting somewhere around here. And this would be up here, we would say we have some new equilibrium. X equilibrium. And so what I was saying about transient analysis is we start from one equilibrium where maybe the mass is being held at the unstretched length, and then we release it and it evolves to some new equilibrium. So it's at t equals 0, it would start at x equals 0, and then it would go through this oscillation. Okay, so that's the transient response. It's the evolution of our system with time from one equilibrium to another. So that's all fine. You could probably be sitting there and saying, well, I understand all that. What does that have to do with the LRC circuit? And so we're going to try to make that connection right now. So what we'll do is we'll draw a free body diagram of the mass on a spring. So free body diagram of the mass on a spring. Okay, so what forces are acting on our mass? Let's remember we're going to take positive x to be down, and let's suppose that instantaneously at the moment that we're drawing right now, the mass happens to be moving downwards. What are the forces acting on it? Gravity is one of them. Okay, so that's a good one. Mg. What else? Yeah, so there's the spring, right? So the spring force. If we're moving down, let's imagine we've moved past the equilibrium, and so the spring force happens to be pulling it up. And so here's kx. What else? There's one more. Yeah, the drag force. And so the drag force is always going to be in the direction opposite of the instantaneous velocity. And so if we happen to choose a velocity down for this diagram, we have a drag force up. So yeah.
Or to go to be buoyant.
Yeah, so there would be buoyancy. Let's assume that for the sake of this argument, the density of our mass is much greater than the density of the fluid, so the buoyancy force is small. But we don't have to do that. We could include that here. I'm just not going to. But you're absolutely right. There would be a buoyancy force. Okay. So the other thing we'll do is we'll assume that the drag force D is given by D is equal to B times V. So it's, in other words, the drag force is proportional to how fast the mass is moving. And experimentally, I'm not going to justify this, but experimentally, this is what is observed when the speeds are relatively slow. Okay, and so this B is just a constant, and it's going to be our drag coefficient. Okay, so there it is. There's our free body diagram. All I'm going to do is I'm going to write down Newton's second law, or the equation of motion for our system. So Newton's second law is that ma is equal to the net force on our system. So m times a is equal to the net force. Well, we took x to be positive down, so mg is a force downwards, and so we'll put that as a positive one. And then we have a drag force and spring force both pointing up, so we'll have a minus kx, and we'll have a minus b times v. All right, and so ma is just the net force, right? That's what Newton's second law tells us. Okay, I mean, maybe you can see already that this is starting to look similar, at least in some respects, to our differential equation for the LRC circuit, because we have something that's proportional to a quantity x, and then we have speed. But how are speed and position related? Derivative. So this is a dx dt. And acceleration is a d2x dt2. So if we rewrite v is dx dt and a is d2x dt2, then okay, well, let's just put it in there. M d2x dt2 is equal to mg, that doesn't change, minus k x, that doesn't change, minus b dx dt. Okay, now what I'll do is I'll put anything that has an x in it on the same side. So I'm going to move this first derivative over here. I'll move the kx over here. And I'll get rid of the coefficients in front of the second derivative just by dividing by the mass. Okay, so we have d2x dt2. And then we're going to bring over the drag force plus b dx dt, but we have to divide by the mass. And then we'll bring over the spring force. So plus k over m, and then we have x. And then that has to be equal to mg, but we're going to divide by the mass so that m cancels. And so what we have now is this equation B. And if we compare it to A, I don't know, can I get it all on there? No, it's not reasonable. A, two derivatives of some quantity, single derivative, no derivatives, and just some coefficients is equal to a constant. Here we have two derivatives of some quantity, a single derivative, and just x with some coefficients equal to a constant. So A and B, we have different symbols, but mathematically, these two differential equations are the same. Okay, did you have a question? No, okay, good. So mathematically, equations A and B are identical. Right, you could have some weird things where you could say, well, what if some of these coefficients are like negative or something like that? If you look physically at the two expressions, there's no reason that we would have a mass or a spring constant or a drag coefficient that is negative. And there's no reason that we would have negative inductance or capacitance or resistance. So all these coefficients are positive. So we just have some positive constants and then a variable and its derivatives in both cases. Okay. So therefore, the solution for x of t in B has this, I guess I should have said it, I should say it the other way. Okay, let's say the solution for q of t in A is of the same form of the, oh yeah, no, that was good. Of the same form as the solution for x of t in B. And we've already sketched out what the solution for B is. It's this damped oscillation. Yeah.
Is it just mathematically equal, or does it have like a physical technical similarity?
Oh yeah, so I mean, what you could think of is, let's take a look at the two, you could build up the analogy, right? So if I had a circuit with capacitance, inductance, and resistance, and I want to compare it to the mechanical analogy where we have, say, some dissipation from a drag coefficient, we have some gravitational potential energy, and we have some elastic potential energy. So which one of R, L, and C is going to be related to dissipation? The resistance, right? Resistance, if I pass current through a resistor, I generate heat. And I generate heat that's, in some ways, the power dissipated would be like I squared R or something like that. So it's, the heat generated is determined by R and the current. In the mechanical analogy, the heat is generated by our drag coefficient B and the velocity. And remember, current is dq dt and velocity is dx dt. So they're very similar. So the other thing we could think about is how we could make analogies between the L and the C. That's a little more difficult, but it's possible. So I think you can build that analogy quite nicely. Yeah. All right. So, So let's go back and let's see if we can push this a little bit further. For the mass on a spring, we can find the final equilibrium position, by, okay, so let's think about this for a second. What's going to happen to the mass a long time after we release it? Is it going to be moving or is it going to be stationary? Stationary. So when it's stationary, what are dx and d2x, dt2? Zero. By setting dx dt, which is equal to v, and d2x dt2, which is equal to a, to be equal to 0. Okay, so let's do that. Let's just rewrite equation B where we put zeros in for this thing. So that would say that K over M times X equilibrium. So this is the equilibrium position a long time after the mass was released. Is just equal to G. And that's all it is. And so therefore, X equilibrium is equal to mg divided by K. So if we go back to our plot here, this X equilibrium we've discovered is mg over K. All right. Now I'm not gonna pretend like our little hand wavy argument, like we're not doing a rigorous calculation. There are things that we don't know about this. So for example, without doing a more rigorous mathematical analysis, we don't know the frequency of these oscillations. We don't know how quickly they're damped away. And we don't know, for example, what is the amplitude of this oscillation just after we release it. So that's all of those details we would have to work out through actual calculations. But we could say something about this system. And one of those things that we could say is the equilibrium position. And that equilibrium position is just an analysis, essentially, of the forces. Okay, for our LRC circuit, we can do a similar thing. For the LRC circuit, we can find the final equilibrium charge on our capacitor by setting I, which is a dq dt, and well, there's no special name for the derivative of the current, so I'll just write it as the derivative of the current or the second derivative of the charge to 0. Okay, and so let's think, what did we have in equation A? We had, we're going to set this to 0, we're going to set that to 0, so we're going to have 1 over LC times Q is V naught over L. And you can see the L's are going to cancel. So set it to 0, let's say in A. And so we have 1 over LC. This is Q equilibrium a long time after we flip the switch up. Has to be equal to V naught, the battery voltage, divided by L. So we'll get rid of that factor of L. And so therefore Q equilibrium is just going to be C times V naught. Okay, and so if we were to plot as a function of time the charge on our capacitor, I'm going to move my axis a little bit here. Here's Q. Here's our time. Something like that. we're gonna have over here is let's see, we're gonna start uncharged at t equals 0. That was our initial condition. And then we're gonna have an oscillation to something like this, and those oscillations die out, and they oscillate about this Q equilibrium. Q equilibrium is equal to C V naught. Okay, and so if we knew this, we could take a derivative of this and deduce the current. And the current would also oscillate, right? Because the current is just the slope of this thing everywhere. It will be shifted in phase, right? Wherever, what would the current be right here at this peak? 0. So wherever we have a node or antinode in our wherever we have a peak or a minimum in our oscillation of the charge, that's where the current would be 0. And wherever we have these crossings of the equilibrium position, that's where the slope is the steepest, either positive or negative. And so that's where we would have the peaks and dips in our current. So it would look the same, it would just be shifted in phase. Okay. You will see this behavior in lab number 4. All right. I want to do one other thing with this analogy. And let's go back to think about the mass on a spring. We have it submerged in this viscous fluid. We pull it down, release it, it oscillates. Those oscillations are damped away. What if I change that fluid from like some light oil that has like a low viscosity, or maybe like an alcohol, right? Alcohol is not that viscous. And I change it to be honey. So now my mass is submerged in honey and it's on a spring. I pull the spring down and I pull the mass down, stretch the spring, and I release it. What does the mass do? So yeah, I think so. The damping, I think what you're saying is the damping is going to increase significantly. Is that right? Would you expect when we release the mass, is it just going to approach the new equilibrium, or will it oscillate past it? What do you think is going to happen?
Probably approach it.
Just approach it, yeah. So it seems like there are kind of different scenarios where the behavior of the system is a little bit different. So mass on a spring, submerged in honey. Okay, so let's draw our mass on a spring. I want to get this about right. So here's T. What we'll start at is our initial equilibrium position, and then, well, we'll say our initial equilibrium was the bottom one, and then when we release it, it goes down to the top one, right? Because we had our X positive pointing down. So we're going to start here, and if we're in honey, this will just slowly approach the new equilibrium. This is called overdamped. It's when we have lots of drag. We can do the same thing in an LRC circuit. How would I increase dissipation in an LRC circuit? Larger resistor. So I could just increase the resistance, and then we'll eventually get this behavior. So instead of honey, if we have this in like alcohol, I don't know how to spell alcohol, then we get the behavior that we were already talking about, where we, oh, I don't love that. Let's do a better job. we get these damped oscillations, and this is called underdamped. There's one more special case, and that special case is how can I approach the equilibrium as fast as possible? Okay, this overdamped in the honey reaches equilibrium without any oscillations, but it takes a long time to get there. The underdamped one overshoots the equilibrium, like it approaches equilibrium quickly, but then overshoots and then oscillates about that. And it doesn't settle to that final equilibrium for a long time. What if I wanted to get to the new equilibrium as fast as possible? Well, what you can do is you can find some optimal damping between under and over damped, and that's called critical damping. And so in the mechanical analogy, we would just be changing the viscosity of our fluid. In our LRC circuit, we'd be tuning the value of the resistance. And this has practical uses. There are circuits or control systems that you can develop to say regulate the temperature. Like imagine you're doing an experiment, you have some sample and you want to measure how that sample behaves as a function of temperature. Maybe you're measuring, it doesn't matter what its property is, thermal conductivity, whatever it is. And you want to know how that thermal conductivity changes with temperature. And so you're going to be constantly changing the temperature of your sample using these control systems. Well, your control system can be underdamped and it'll oscillate about the new equilibrium temperature before finally settling on it. It could be overdamped, or it takes a long time to approach that equilibrium, or it could be critically damped, where you quickly reach that new equilibrium in an optimal least amount of time, and that's called critical damping. And in critical damping, what happens is you have just one small overshoot until you settle in. Oh, I'm going to adjust this a little bit. I want the critical damping one to look like it reaches equilibrium the fastest. So this is critical damping, which is the fastest approach. Fastest to reach equilibrium, fastest to reach equilibrium. And this has some intermediate damping, right, between the underdamped and overdamped cases. Okay. What we'll focus on in lab 4 is the underdamped case. That's the most interesting one where you see a lot of those oscillations, and we'll be able to relate it to what we'll eventually find is a resonance behavior, and that resonance frequency is going to be related to the frequency of these oscillations. Okay, so that's something to look forward to. All right, any questions about this little analogy here? Yeah.
Is there a term for instead of drag, but like acceleration in the direction of the I guess current?
An acceleration in the direction of the current.
So that instead of damping the
Oh, like you want a growth in the oscillations? Yeah, so if you wanted to do that, you're gonna have to inject energy into your system. So you're gonna have to drive it with something like a function generator or something like that. So you can do that, but not with just a battery. Yeah.
is it this like a specific part of the system that makes the charge oscillate, or in all terms oscillate when you put it into the mechanic is the spring, right?
Yeah, so in what we'll find is that in a circuit, in an electronics context, whenever you have an inductance and a capacitance, you'll have a resonance frequency. And you almost always have that, even if you don't explicitly put an inductor and a capacitor in your circuit. Let's imagine you didn't put an inductor here. Your circuit still has a loop and it still has a current going around that loop. So there's still some parasitic inductance involved in your circuit. And so this would still have a resonance frequency. We will eventually get there, but what it's going to turn out is that we're going to define what's called the impedance of the capacitor and the inductor, and the resonance condition, the oscillation, is a result of these two canceling each other at a specific frequency. So we'll get there in a few weeks. Yeah. Okay, good. So what I want to do in the last 4 minutes is I just want to set up the problem that we're going to solve on Monday. So next time we'll analyze the RC series circuit. And a lot of what we've done about this discussion today, we can use when talking about our RC circuit. I'll draw it using a similar geometry. What we're going to have is our switch. We'll have our resistor. We'll have our capacitor. But I'm not going to put in the inductor. And we'll have a down position for our switch. So again, we will start with the same situation. Start with switch down such that Q equals 0 and I equals 0. So those are our initial conditions. At T equals 0, we flip the switch up. We want to find Q of T as the system approaches the new equilibrium. Okay, so let's do the Kirchhoff loop rule when we're with the switch up. Okay, so with the switch up, we're going to go around this outside loop here. And the first thing we do is we cross our battery. So we get a voltage V naught. Then we cross the resistor, and then we cross the capacitor. The voltage across the resistor is I times R, or R dQ dt. The voltage across the capacitor is Q divided by C. And that has to be equal to 0. What I'm going to do is I'm going to rearrange this in a similar way that we did for the LRC circuit. I'm just going to divide by R so that we don't have a coefficient in front of the dq dt. And I'll move these things with negative signs to the other side. And so the result is dq dt. So I divide by R, then I get plus 1 over RC times Q is equal to V naught. And so this is a first order differential equation. We want to solve for Q of T.
You don't R under the V naught, right?
Yes, I do. Thank you very much. You're right. Okay, good. We have 1 minute. So somebody tell me, what is the equilibrium charge going to be a long time after the switch is flipped up? How would you find it? Yeah, and so what did you do? You set dq dt equal to 0. A long time after the switch is up, dq dt is equal to 0. So that's when we reach the new equilibrium. And so therefore, 1 over RC, Q equilibrium is equal to V naught over R. We cancel the R's. And so therefore, Q equilibrium is equal to C times V naught. That's the same thing we had for the LRC circuit. So if we were to plot Q as a function of time, this will be the last thing I draw. What we're going to know is that at t equals 0, our initial condition was that there was no charge on our capacitor plates at all. And so we have to start here. And then a long time after the switch is closed, when we have no current in our circuit, we reach some Q equilibrium. And that is going to be sitting right here. And so what we're interested in is how do we connect these 2 points? And the way we're going to discover what happens, you may already know the answer, which is fine. We're going to solve this differential equation. And that's what we'll start with on Monday. All right, thank you very much. Have a good weekend. Sorry, well, we have lab tomorrow, so I'll see you in the lab. Please have your lab